A single blip on a chart once sent scientists into a frenzy. For decades, our most powerful telescopes have been eavesdropping on a universe crackling with whispers and screams we cannot yet understand. This is a journey through 25 of the most baffling signals ever captured from the void. You will discover the true stories behind legendary cosmic mysteries, from a burst so powerful it was scribbled WOW to repeating patterns that defy all natural explanation. Was one signal really from our closest star, and what monstrous object in our own galaxy finally gave up a secret? By the end, you will see the cosmos not as a silent night sky, but as a chaotic radio station broadcasting enigmas on every frequency. We begin with a printout from 1977 that changed everything. What do you believe is waiting for us in the dark? The printout from the Big Ear radio telescope is a single line of data, yet it holds more cosmic weight than entire volumes of star charts. On August 15, 1977, a radio telescope at Ohio State University, quietly scanning the sky, caught a 72-second burst of intense noise. It was so powerful, so anomalous, that when astronomer Jerry Amon reviewed the computer printout days later, he simply circled the sequence of letters and numbers and wrote one word in the margin: wow. The signal itself was coded as 6EQUJ5, a notation representing its incredible strength. For that brief minute, it outshone the background noise of deep space by a factor of 30. It came from the direction of the constellation Sagittarius, a dense region of the Milky Way, and it was concentrated on one specific radio frequency, the so-called hydrogen line, which many scientists had theorized would be a logical channel for interstellar communication. Think of it like hearing a single, crystal-clear shout of your own name in a crowded, roaring stadium. That is what the Big Ear heard. The hunt for a repeat began immediately and has never stopped. For decades, telescopes have aimed back at that same patch of sky, listening with far more sensitive equipment, hoping for another whisper, another clue. Nothing. The signal has never been heard again. This single, unrepeatable event is what makes it so compelling and so frustrating. Natural cosmic phenomena like pulsars or stellar flares repeat. They have rhythms. The wow signal was a one-time shout into the void. Was it a message that swept past us, never to return? Was it a bizarre, never-before-seen natural event? Its solitary nature has cemented its legacy as the ultimate cosmic mystery, a ghost in the machine of astronomy that continues to haunt our search for answers. While the wow signal remains a solitary enigma, the cosmos soon revealed it was capable of something even stranger, a whole new class of scream. In 2007, astronomers sifting through archived data from a radio telescope in Australia found a spike of energy so brief it had almost been overlooked. It lasted just 5 milliseconds, a flicker in cosmic time, but it carried the power of 500 million suns. This was the first recognized fast radio burst, an FRB. Imagine the energy our sun releases over 80 years, compressed into the time it takes a camera flash to fire, and beamed across billions of light years. The discovery was met with profound skepticism. Could it be a glitch, some local interference from Earth, perhaps a microwave oven on the observatory campus? But then another was found, and another. Each one was a singular, catastrophic event, a flash of radio light from so far away it had traveled across half the age of the universe to reach us. The central mystery became terrifyingly clear. What natural engine in the cosmos could possibly produce such an impossibly brief, unbelievably energetic flash? It defied all known physics. A supernova takes weeks to unfold. A pulsar's beam is a steady, predictable lighthouse. These were something else entirely, cosmic lightning bolts from the deepest voids, pointing to forces and objects we had yet to even dream of. The hunt was on to catch one in the act. The solitary blasts were terrifying, but a repeating signal was something far more useful. In 2016, astronomers made a discovery that cracked the FRB mystery wide open. A source designated FRB 121102, first detected in 2012, did something extraordinary. It flashed again and then again. This was not a one-time cosmic catastrophe. This object, whatever it was alive. It was a repeater, located in a tiny, faint dwarf galaxy, an astonishing 3 billion light-years from Earth. This faint smudge of stars became the most important address in the universe for understanding these bursts. The simple fact of repetition changed everything. It immediately ruled out theories involving single, destructive events like the collision of two neutron stars or the final death cry of a black hole. You cannot blow up the same star twice. Instead, the repeater pointed toward objects that could survive their own outbursts, cosmic engines capable of firing off multiple catastrophic blasts. The prime suspect became a type of neutron star called a magnetar, a city-sized remnant of a supernova wrapped in a magnetic field so intense it could strip the information from a credit card from halfway across the Milky Way. Theorists suggested that starquakes on the surface of a young, hyperactive magnetar could potentially generate these immense, sporadic radio shrieks. Yet the sheer power of the bursts, visible across 3 billion light-years, pushed even this extreme explanation to its limits. This tension between a known object and an unknown output opened the door for more speculative ideas. Could the precision and repetition hint at something artificial? A civilization, for instance, might use a powerful, directional burst to propel a light-sail spacecraft across interstellar distances, a flash we would see each time the beam swept past our planet. While natural explanations like magnetars remain far more likely, the repeater did one crucial thing. It gave scientists a target. They could now watch and wait, knowing the source was still there, still active, ready to reveal more of its secrets with every new flash from the deep. 3 billion light-years is a distance the human mind cannot truly grasp, but our own galactic backyard is a place we can understand. The shock came in 2021, when a new fast radio burst was traced not to a distant, nameless galaxy, but to a familiar object right here in the Milky Way. Designated FRB 2020-00120E, its origin was pinpointed with stunning precision to a globular cluster in the galaxy Messier 81, a mere 12 million light-years away, which in cosmic terms is practically next door. This was not just any location, it was an ancient swarm of stars where new ones are rarely born. The most likely culprit hiding there was a magnetar, but one with a bizarre and violent past. Astronomers suspect this particular magnetar was not born from a regular supernova, but was forged in the collision of two white dwarf stars, a rare and cataclysmic event that left behind an ultra-dense, intensely magnetic zombie star. For the first time, we had a face to put to the name. This detection was the smoking gun, the long-sought proof that at least some of these universe-spanning screams are indeed produced by magnetars, those unimaginably dense, spinning magnets left behind when giant stars die. It solved a major piece of the puzzle, confirming a leading theory. Yet, in classic cosmic fashion, it immediately raised a host of new questions. If magnetars in our own neighborhood can produce FRBs, why are the ones from distant galaxies so phenomenally more energetic? The burst from Messier 81 was thousands of times weaker than those coming from billions of light-years away. This suggests a terrifying diversity in the sources. Perhaps younger, more violently active magnetars in the early universe were capable of far greater outbursts. Or perhaps magnetars are just one member of a whole family of cosmic monsters capable of generating these flashes. The discovery of the galactic intruder did not close the case. It simply proved that one of the prime suspects definitely lives among us, while hinting that far more dangerous versions might be lurking in the deep dark. Long before the term fast radio burst was ever coined, the very first one was already waiting in a forgotten data tape. The story begins not with a live detection, but with a retrospective discovery in 2007. Astronomer Duncan Lorimer and his student David Narkevic were sifting through old observations from the Parkes Radio Telescope in Australia, data recorded back in 2001. Their goal was to find new pulsars, the steady, ticking remnants of dead stars. Instead, they found a ghost. Buried in the noise from a single observation of the Small Magellanic Cloud was a 5-millisecond spike of radio energy so intense it saturated the telescope's receiver. It was a blast of pure power with a very strange signature. Its signal showed a clear effect called dispersion, where lower radio frequencies arrived slightly later than higher ones, a telltale sign that the waves had traveled through the diffuse gas of intergalactic space. The amount of dispersion was staggering. It indicated this burst did not originate in our galaxy or even in the nearby Magellanic Cloud. It had come from billions of light years away. Calculating the energy required was humbling. In those few milliseconds, this unknown source released more energy than our Sun does in 30 years. Yet, when it was first proposed, the astronomical community was deeply skeptical. The simplest explanation seemed to be that it was some form of local interference, a glitch from an earthly source, perhaps a passing satellite or even a piece of electronic equipment on the ground. The idea that such a brief, powerful signal could come from halfway across the universe seemed to defy physics. It was so extraordinary that many dismissed it as an artifact, a mistake in the data. This single event, now known as the Lorimer Burst, languished for years as a curious anomaly. Its true importance only became clear when other, similar bursts were finally discovered. In hindsight, that one archival blip was the Rosetta Stone. It was the progenitor, the first undeniable evidence of a phenomenon so violent it reshaped our understanding of the cosmos's most energetic events. The lesson it taught was profound. The universe's greatest secrets are not always announced with fanfare. Sometimes they hide in plain sight, buried in old data, waiting for someone to look at the noise and see the signal. The Lorimer Burst was a lonely ghost, but a new telescope was about to turn the whispers into a roar. Perched in the dry hills of British Columbia, the Canadian Hydrogen Intensity Mapping Experiment, or CHIME, looks nothing like a traditional dish. It is a sprawling array of 4 half-pipe cylinders, like massive snowboard ramps turned to the sky. Its design is its genius. Instead of moving to point at targets, CHIME stares fixedly at a huge strip of sky as the Earth rotates, drinking in radio waves across an enormous range of frequencies. This makes it the perfect net for catching fleeting, unpredictable flashes. When CHIME came online, it did not just find a few new fast radio bursts. It unleashed a flood. Where before we had catalogued a few dozen, CHIME began detecting hundreds. Each new detection was a data point, and with enough points, patterns began to emerge from the chaos. Scientists could finally start to categorize them. Some bursts were clean and sharp, others were smeared and scattered. Some came from the deep, ancient universe, others from more recent cosmic epochs. Crucially, CHIME began finding repeaters at an astonishing rate, proving that repeating sources were not rare exceptions, but a common feature of this bizarre phenomenon. This statistical treasure trove did something even more profound. Each fast radio burst carries a hidden fingerprint in its dispersion, the smear caused by traveling through the thin gas between galaxies. By measuring this smear from thousands of bursts across the sky, astronomers can use them as cosmic probes. Imagine you are in a dense fog and you hear bells ringing at different distances. By noting how muffled each bell sounds, you could start to map the density of the fog around you. That is what CHIME flood of data allows. Each FRB illuminates the invisible web of matter it passed through on its billion-year journey. We are now using these titanic, mysterious screams to chart the vast, empty oceans of intergalactic space, turning cosmic catastrophes into tools for mapping the architecture of the universe itself. The flood of data from deep space makes every anomaly precious, yet the greatest temptation is to find meaning where none exists. In late 2020, the Breakthrough Listen project, a monumental scientific effort to scan the cosmos for technosignatures, detected a signal that sent a genuine shiver through the community. It was a narrowband radio signal, a single pure tone at 982 MHz, and it appeared to originate from the direction of Proxima Centauri, the closest star to our own Sun and host to a known rocky planet. This candidate, named BLC-1, checked several tantalizing boxes. It was narrow, like a focused radio carrier wave, not the broad, messy emission of natural cosmic objects. It drifted in frequency in a way consistent with a signal coming from a planet orbiting a star. For a brief, electrifying moment, it seemed like the discovery humanity had dreamed of for a century might have come from our very own celestial backyard. The excitement was palpable but rigorously contained. The team did not announce a discovery, they announced a candidate requiring exhaustive investigation. For months, scientists performed the meticulous forensic work of modern SETI. They pointed other telescopes at Proxima Centauri, listening again on that same frequency. They analyzed the signal for any modulation, any hint of encoded information. They scrutinized every possible source of local interference, from passing satellites to ground-based electronics. The ultimate conclusion was a sobering lesson in cosmic patience. The signal, while intriguing, was almost certainly human-made interference, likely from a malfunctioning electronic device here on Earth that had been reflected off some piece of space debris or a satellite. Its apparent drift and direction were a cruel coincidence, a perfect alignment of mundane factors mimicking an interstellar broadcast. BLC-1 did not vanish into the noise like the WOW signal, it was explained away. Yet its legacy is profound. It proved our detection methods are sensitive enough to pick up extremely subtle candidate signals, and more importantly, it demonstrated the rigorous, skeptical process required to investigate them. In the search for cosmic company, hope must always be tempered by the hardest task of all, proving to ourselves that we are not just hearing an echo of our own noise. A signal does not need to be powerful to ignite fierce debate. In the early 2000s, a project called SETI at Home harnessed the idle processing power of millions of personal computers worldwide, creating a virtual supercomputer to sift through radio telescope data. It was within this digital haystack that a curious needle emerged, catalogued as SHB-02+14A. This signal was faint, almost whisper-quiet, but it possessed two haunting characteristics. First, its frequency hovered near 1,420 MHz, the fundamental emission line of neutral hydrogen, the most common element in the universe. This is a frequency many scientists have suggested would be a logical calling card for a technological civilization, a sort of universal watermark. Second, its apparent source was a seemingly empty point in the sky between the constellations Pisces and Aries, a region devoid of any nearby stars. For a moment, it seemed like the perfect candidate, a whisper on the right channel from the cosmic wilderness. The controversy, however, lay in its behavior. The signal was not a steady tone, it drifted. Its frequency shifted slightly over time, which could be explained by the Doppler effect caused by a signal originating from a planet orbiting a distant star. Yet this drift was erratic, and the signal itself was so weak it faded in and out of detectability. To its proponents, these very flaws made it intriguing, as a distant, shaky transmission from a wobbly world might behave exactly this way. To its detractors, these were fatal flaws. The signal's weakness and instability pointed overwhelmingly to a much more mundane source, terrestrial radio frequency interference, perhaps a harmonic from a passing satellite or some piece of poorly shielded electronics on the ground, reflected and distorted until it mimicked something extraordinary. The story of SHB-02+14 is not one of triumphant discovery or heartbreaking mystery like the WOW signal. Instead, it is a masterclass in the grinding, meticulous work of modern SETI. It represents the fine, often frustrating line scientists must walk every day, separating a potential whisper from the stars from the relentless, buzzing static of our own technological civilization. In this field, extraordinary claims require not just extraordinary evidence, but evidence that remains extraordinary after every conceivable earthly explanation has been exhausted. This signal, in the end, could not pass that ultimate test. The search for signals often focuses on what we can hear, but some of the greatest mysteries are written in the light we can see. In the constellation Cygnus, a star named KIC 8462852, later known as Tabby Star, began behaving in a way that defied every textbook. Data from the Kepler Space Telescope revealed its light was not just dipping in the regular, gentle rhythm of an orbiting planet. It was plummeting. The star would dim by staggering amounts, up to 22%, in chaotic, asymmetrical patterns that lasted for days or weeks. No known natural phenomenon could explain it. A planet, even a giant one, would block only about 1% of a star's light. This was something monstrously large and irregularly shaped passing in front of the star. The most tantalizing and controversial hypothesis came from astronomer Jason Wright, who suggested the signature could fit a swarm of artificial structures, an alien megastructure like a Dyson swarm under construction, designed to harvest a star's energy. The idea of a civilization so advanced it could dismantle planets to build a shell around its sun captured the public imagination like no signal ever had. Suddenly, a deep cosmic mystery was not just for scientists. The star's discoverer, Tabitha Boyajian, and her team turned to crowdfunding for follow-up observations, and thousands of people donated, becoming active participants in the hunt. This public engagement marked a revolution. For years, telescopes around the world monitored Tabby Star, and a pattern finally emerged. The dimming was not equal across all colors of light. It was more pronounced in blue light than in red. That single clue was decisive. Solid structures, whether planets or alien megastructures, would block all colors equally. Dust, however, scatters blue light more effectively. The bizarre light curves were almost certainly caused by clouds of fine, circumstellar dust, possibly from the breakup of a comet or a moon, creating a chaotic, evolving veil around the star. While the alien megastructure theory faded, the legacy of Tabby Star is permanent. It proved that the most exciting discovery in astronomy is not always an answer, but a question so compelling it mobilizes the world to look up and wonder together at what might be hiding in the familiar flicker of a distant sun. The hunt for alien megastructures taught us to question our assumptions, but the ultimate lesson in cosmic humility arrived with a steady, metronomic beat. In 1967, a young graduate student named Jocelyn Bell Burnell was meticulously analyzing reams of chart paper from a new radio telescope near Cambridge. Her task was to study quasars, but she noticed a peculiar bit of scruff, a faint, repeating signal that appeared and disappeared with the rotation of the Earth. It was not a broadcast from a known satellite or any earthly source. With painstaking care, she tracked it, and the signal resolved into something astonishing, a series of radio pulses so perfectly regular they defied belief. They arrived every 1.337 seconds with a precision that rivaled the finest atomic clock on Earth. The immediate, electrifying thought among the small team was that they had found something artificial. In a moment of half-serious, half-anxious speculation, they even labeled the source LGM1 for Little Green Men. The idea that it could be a beacon from an extraterrestrial civilization was not a joke. It was a genuine, terrifying possibility that had to be considered. The profound implications were staggering. Here was a signal that behaved exactly how scientists predicted an interstellar marker would behave, a clear, unambiguous signpost in the noise. The team kept the discovery secret for months, wrestling with the responsibility. What if it was true? How do you announce to the world that you might have found another intelligence? The resolution came not from decoding a message, but from finding more of them. Jocelyn Bell Burnell soon discovered a second, similar pulsing source in a completely different part of the sky. Then a third, the chance of 3 separate civilizations all building identical galaxy-spanning beacons and aiming them at an insignificant planet like Earth was vanishingly small. The truth was even more extraordinary. They had discovered pulsars, the lighthouses of the cosmos. These were not alien beacons, but the corpses of massive stars. A pulsar is a neutron star, a ball of matter so dense that a teaspoonful would weigh 1 billion tons, spinning at incredible speeds and beaming radiation from its magnetic poles. As it spins, the beam sweeps across space like a cosmic searchlight, and if it points toward Earth, we see a flash with every rotation. The perfect clockwork was not intelligence, but physics pushed to an extreme. The story of LGM-1 is a cornerstone of modern astronomy, a beautiful irony where the search for artificial life led to the discovery of one of the universe's most natural yet most bizarre objects. It taught the SETI community an invaluable lesson. The universe is capable of producing signals of breathtaking regularity and precision all on its own. Before we can claim we have found a message, we must first prove we are not just listening to the heartbeat of a dead star. The bizarre light curves of Tabby Star were not gentle slopes but sheer cliffs. Kepler's data revealed not one but several catastrophic dimming events. In 2013, the star's light dropped by a staggering 15% over just a few days, an amount that would require an object nearly half the width of the star itself. Later, an even more dramatic 22% dip was recorded. This was not a neat, repeating transit like a planet. It was jagged, asymmetrical, and profoundly messy, as if something with a complex, irregular shape was drifting erratically through the star's line of sight. To explain such chaos, astronomers had to think beyond simple spheres. The first natural suspect was a swarm of exocomets. Imagine a family of icy bodies, perhaps disturbed by a passing star plunging toward their sun. As they approach, they begin to vaporize, trailing enormous clouds of dust and gas behind them. A giant, fluffy comet with a vast, ragged tail could indeed block starlight in an irregular pattern. If a whole procession of such comets, each with different sizes and tails, passed in front of the star, it could create the chaotic sequence of dips Kepler observed. Another hypothesis pointed to circumstellar debris from a colossal collision. Perhaps 2 planets or a planet and a large moon had smashed together in the star's system. The resulting cloud of shattered rock and dust spread across a wide, clumpy orbit would create a persistent, evolving veil that would dim the star unevenly for centuries. Some scientists even proposed intrinsic stellar variability, suggesting the star itself might be undergoing rare and violent magnetic convulsions, though no known star behavior matched the sheer depth of these dimmings. Each natural explanation had strengths but also holes. A comet swarm large enough to cause a 22% dip is almost unimaginably vast. A planetary collision is a spectacularly rare event we would be lucky to witness. Yet, for the scientific community, even an incredibly rare natural event is always more probable than an unprecedented artificial one. The alien megastructure hypothesis, while capturing global imagination, serves a specific and vital purpose in science. It is what astronomers call a hypothesis of last resort. It is only entertained when every single natural explanation, no matter how unlikely, has been exhausted and found wanting. For Tabby Star, the crucial color clue, the fact that blue light was blocked more than red, provided the key evidence that dust, not solid megastructure, was the culprit. This does not make the star any less mysterious. It simply means the mystery resides in the realm of extreme astrophysics, not alien engineering. The true power of Tabby Star was that it forced us to expand our understanding of what is naturally possible, revealing that a star's story can be written not just in light, but in shadow, dust, and celestial wreckage. A sun-like star just 95 light-years away seemed to send us a direct call. In 2016, the Ratan 600 radio telescope in Russia detected a strong, intriguing signal from the direction of HD 164595, a star nearly a twin of our own Sun and known to host at least one Neptune-sized planet. The signal was a powerful burst at 11 gigahertz, lasting only a couple of seconds. What made it so compelling was a simple calculation of its potential. If the signal had been broadcast in all directions like a radio station, it would have required an energy output far beyond anything humanity could muster. But if it were a focused, narrow beam deliberately aimed at our solar system, the power required dropped to a level comparable to our own civilization's total energy use. For a brief moment, it felt like a plausible calling card, a targeted hello from a technological neighbor. The excitement, however, was intensely short-lived. The scientific community, now well-versed in the forensic work of signal analysis, immediately began the process of elimination. The first and most critical clue was the signal's frequency. 11 gigahertz is a band heavily used by military and civilian satellites here on Earth. This raised an immediate red flag. Further investigation revealed the signal was never detected again by any other telescope, despite repeated attempts to listen. The most likely explanation, though mundane, was compelling. It was almost certainly a burst of terrestrial interference, most plausibly from a secretive military satellite passing through the telescope's field of view. The signal from HD 164595 serves as a perfect modern parable for the search. It underscores a frustrating new reality of the 21st century. Our sky is now filled with our own technological chatter, a buzzing halo of satellites and transmissions that can perfectly mimic the signature of an interstellar beacon. Every potential signal must now run a gauntlet of verification, not just against natural cosmic phenomena, but against the ever-growing electronic noise of our own species. The search is no longer just about listening to the quiet of the universe, but about learning to recognize our own reflection in the static. The Ratan 600 telescope in Russia is a colossal ring of radio reflectors, a stationary giant that scans the sky as the Earth turns. Its detection from HD 164595 was not a whisper, but a sharp, powerful spike at a frequency of 11 gigahertz. This specific frequency is part of the microwave window, a quiet band of the spectrum where cosmic noise is minimal and which many have considered ideal for interstellar communication. The signal's strength and its brief, 2-second duration were the technical details that sparked immediate analysis. Scientists quickly calculated that if this was an omnidirectional broadcast, a signal blasting in all directions, the energy required would be colossal, on the scale of a Kardashev Type 2 civilization capable of harnessing the total power of its star. However, if it was a narrow, targeted beacon aimed precisely at our solar system, the power needed fell dramatically to something within the conceivable reach of an advanced society. This mathematical fork in the road is what transformed a single blip into a global event. The international response was swift and coordinated. Within days, the Allen Telescope Array in California and the Green Bank Telescope in West Virginia were both pointed at HD 164595, listening intently on that same 11 gigahertz frequency and across a wide range of others. The Breakthrough Listen project added its immense data collection power to the effort. The world's most sensitive ears were all tuned to the same cosmic channel, waiting for a repeat for confirmation for a pattern. The result was a profound and definitive silence. Not a single follow-up pulse was ever heard. This non-repeatability is the ghost that haunts the search for extraterrestrial intelligence. A signal that cannot be verified, that vanishes as quickly as it appears, remains forever in the realm of tantalizing maybe. It becomes a story of interference, a satellite pass, or an unexplained glitch. The international effort on HD 164595 did not find aliens, but it demonstrated something equally important, a new global protocol for skepticism. When a candidate signal emerges, the entire astronomical community can now mobilize in real time, subjecting it to the most rigorous possible test, the test of time itself. The silence that followed was not a failure, but a necessary step in the meticulous process of listening to a universe that is far noisier and far more cunning than we ever imagined. The search for cosmic signals is a constant battle against our own reflection, a lesson driven home by a bizarre family of imposters. For years, astronomers at the Parkes Radio Telescope in Australia had been detecting strange, fleeting bursts that looked almost exactly like the distant fast radio bursts they were hunting. They called them Puritans after a mythical winged elk that casts the shadow of a man, a perfect name for signals that looked cosmic but were something far more ordinary. These bursts had the same brief, intense signature, and most convincingly, they displayed that telltale smear of dispersion, the fingerprint of radio waves traveling through vast distances of interstellar gas. They seemed to be coming from deep space, adding to the growing catalogue of cosmic mysteries. Yet something was off. Unlike true FRBs, which appeared randomly from all over the sky, the Puritans were always clustered around the telescope itself. They seemed to originate from somewhere on the ground or just above it. The detective work began with meticulous logging. Astronomers noted the times and dates of every Puritan detection, searching for a pattern hidden in the chaos. A breakthrough came when someone cross-referenced the logbook with the observatory's daily schedule. The Puritans were not random. They occurred almost exclusively during weekday daylight hours, and they clustered around a very specific time, lunchtime. The final clue was the source of the dispersion. True dispersion happens in the thin plasma of deep space, but a similar effect can be created if a radio signal passes through a dense, localized plasma right here on Earth. The solution was both brilliant and hilarious. The culprit was the observatory's staff kitchen microwave oven. When someone opened the microwave door before the timer had fully finished, the magnetron, the device that generates the microwaves, would emit a final, brief burst of radio frequency interference. This burst would shoot out of the door, reflect off the observatory's metal structures or the ground, and travel a short, complex path back up into the giant dish of the telescope itself. That short, multi-path journey through the air mimicked the dispersion signature of a billion light-year voyage. The mighty Parkes telescope, one of humanity's greatest ears on the cosmos, had been eavesdropping on the impatient hunger of its own caretakers. The Puritans are now a celebrated cautionary tale, a reminder that before we can hear the universe, we must first learn to silence the echoes of our own mundane world. The heart of our own galaxy is a place of profound and violent beauty. While radio telescopes listen for whispers, other instruments capture its furious, silent screams. From the core of the Milky Way, two vast structures balloon outward, each stretching 25,000 light-years from the galactic plane. These are the Fermi bubbles, first mapped in gamma rays by the Fermi Space Telescope. They are colossal, symmetrical lobes of ultra-high energy radiation, a pair of ghostly orbs that dwarf our entire galaxy's visible disk. Their very existence suggests a titanic eruption from the supermassive black hole, Sagittarius, a star, sometime in the last few million years. Imagine a dormant volcano the size of a continent that, in a single catastrophic event, belched out enough energy to create two clouds larger than the continent itself, and those clouds are still glowing with the heat of that ancient fury. That is the scale of the Fermi bubbles. They are not signals in the traditional sense, but they are a permanent, blazing signpost of a cataclysm we missed, a testament to the violent adolescence of our own galactic center. Orbiting perilously close to that same monster black hole is another class of enigma, the G objects. These appear as faint, dusty clouds in infrared light, but they move like dense stars. They follow elongated orbits that bring them screaming close to the black hole's event horizon, yet they somehow survive the encounter without being completely shredded. The leading theory is that each G object is a binary star system that merged under the black hole's immense gravitational pull, the collision cloaking the new, larger star in a thick shroud of gas and dust. They are cosmic phantoms, behaving as neither pure gas nor pure star, but as something unsettlingly in between. These phenomena from our galactic core remind us that the greatest mysteries are not always billions of light years away. They are unfolding right now in our own celestial city center, in forms of energy and matter so extreme they continually rewrite the rules of physics in our own backyard. Perhaps the most elusive quarry in all of modern physics is dark matter. This invisible substance, which outweighs all the stars and galaxies we can see by a factor of 5, has never been directly observed. We only know it exists by the gravitational grip it holds on galaxies, a ghostly hand shaping the cosmos from the shadows. In 2014, a team of astronomers thought they might have finally heard its whisper. Using data from the European Space Agency's Planck satellite, which mapped the cosmic microwave background, the researchers reported an anomalous spike of radio emission coming from the hearts of several distant galaxy clusters. This wasn't a brief burst, but a faint, persistent hum at a very specific frequency. The extraordinary claim was that this hum could be the signature of a hypothetical dark matter particle called the action. According to theory, actions in the presence of the immensely strong magnetic fields found in galaxy clusters could convert into photons of radio light. If true, this faint signal would be the first direct evidence of the universe's hidden skeleton, a glimpse of the ghost itself. The scientific community reacted with a mixture of intense excitement and profound skepticism. Extraordinary claims demand extraordinary verification, and this was as extraordinary as it gets. Immediately, other teams rushed to their own data archives, pointing different radio telescopes at the same clusters, searching for that same telltale hum. The process was meticulous and public, a global effort to either confirm a revolution or expose a mistake. One by one, the results came back. The independent teams, using more sensitive instruments and refined analysis, found nothing. No anomalous radio hum, no action signature. The original signal, it seemed, was likely a subtle artifact of the complex data processing, a mirage created when subtracting the bright foreground emissions of our own galaxy. The consensus turned to skepticism. While the action remains a compelling candidate, that particular hopeful signal faded into the background noise of might-have-beens. Yet this story is not one of failure. It is a masterclass in how science self-corrects. A bold claim was made, it was tested by the entire community with ruthless rigor, and it was found wanting. That process, that collective march from excitement to skepticism, sharpens our tools and refines our questions. It forces theorists to propose more testable models and observers to design even more sensitive experiments. Each dead end, each ghost signal that vanishes under scrutiny, clears the path a little more, bringing us closer to the day when a real signal, one that can survive every test, finally emerges from the dark. Przybylski's star burns with a secret written in impossible light. This faint, unassuming point in the constellation Centaurus is a chemically peculiar star, but that description is a profound understatement. When astronomers analyze its spectrum, the unique fingerprint of light that reveals its chemical composition, they find lines that simply should not be there. The star's atmosphere appears to contain promethium, a radioactive element with no stable isotopes. Promethium atoms decay away completely in just a few hundred years. Its presence means this element must be actively produced right now, in or around the star, and constantly replenished. That alone is bizarre, but the list does not stop there. The spectrum also suggests the presence of other short-lived, heavy radioactive elements like actinium, protactinium, and even einsteinium. These are elements forged in the most violent nuclear furnaces imaginable, and they vanish on cosmic timescales. Seeing them in the atmosphere of a star is like walking into an ancient forest and finding the still warm embers of a campfire that was lit yesterday. The natural explanations are as extreme as the data. One theory suggests the star is wandering through the debris cloud of a very recent supernova, bathing in the freshly synthesized radioactive fallout of a neighboring star's death. Another posits that Przybylski's star is an intensely magnetic oddball, a type of star where nuclear processes on the surface, rather than deep in the core, might somehow cook up these bizarre elements in a process we do not yet understand. Then there is the most speculative idea, the one that captures the imagination. Could the light we see be polluted? Imagine an advanced civilization that has mastered nuclear fission or fusion, perhaps on a planetary scale. Their spent nuclear fuel, their technological waste, would be rich in these very radioactive, short-lived isotopes. If a planet in that system met a catastrophic end, perhaps through a collision or a deliberate dismantling, the resulting debris field falling into the star could temporarily contaminate its outer layers with this unmistakable signature. It is the cosmic equivalent of testing the soil downstream from a factory and finding traces of a synthetic chemical that only exists because someone manufactured it. Of course, Occam's razor suggests a natural, if utterly unknown, astrophysical process is at work. Yet Przybylski's star endures as a favorite for exotic hypotheses precisely because every natural explanation strains credibility in its own way. It stands as a permanent reminder that sometimes the universe presents us with a chemistry set that defies our current catalog of ingredients, daring us to consider that the most alien signatures might not be signals we hear, but elements we can see burning in a star's heart. The chemistry of a distant star is one thing, but a visitor from another solar system is a mystery we could almost touch. In October 2017, the Pan-STARRS telescope in Hawaii spotted a faint point of light moving at breathtaking speed. Designated 1I/2017 U1, it was soon given a name, Oumuamua, Hawaiian for scout. Calculations of its trajectory were unequivocal. This object was not from here. Its hyperbolic path and incredible velocity meant it was not bound by the sun's gravity. It was a tourist passing through our solar system after a journey that likely lasted millions of years through the void between stars. As telescopes around the world swiveled to track it, the data that came back was profoundly strange. First was its shape. Based on extreme variations in its brightness, astronomers deduced it was not round. It was elongated, perhaps 5 to 10 times longer than it was wide, tumbling end over end through space like a cosmic cigar. Then came the real shock. As Oumuamua sped away from the sun, its trajectory was being minutely tracked. The laws of celestial mechanics are precise. An object's path is dictated by the gravitational pull of the sun and planets. Yet Oumuamua was not following that predicted path perfectly. It was accelerating ever so slightly as it departed. Something other than gravity was giving it a tiny push. For comets, this is common behavior. As a comet's icy surface heats up near the sun, it releases jets of gas and dust, a process called outgassing. This acts like a natural rocket engine, altering the comet's orbit. The problem was, Oumuamua showed no visible signs of outgassing. No surrounding cloud of gas, no dusty tail streaming behind it. It appeared as a bare, dark rock. So what was pushing it? The scientific community scrambled for a natural explanation. Perhaps it was outgassing after all, but from water ice hidden beneath an unusual, carbon-rich crust that left no visible trail. Maybe it was releasing pure hydrogen gas, invisible to our telescopes, boiled off from ice deep within its core. Each theory was an attempt to fit this unprecedented data into the known catalog of solar system objects, a cosmic shoehorn for an object that refused to fit. Into this debate stepped Harvard astronomer Avi Loeb with a far more provocative hypothesis. He suggested the acceleration could be explained if Oumuamua was extremely thin and lightweight, like a sheet of material less than a millimeter thick. Such an object would be pushed by the radiation pressure of sunlight itself, a natural photon sail. On Earth, we are experimenting with this very technology, designing thin, reflective light sails to propel tiny spacecraft without fuel. Loeb's argument was not that Oumuamua was definitely artificial, but that its peculiar combination of characteristics, its strange shape, its lack of a coma, and its non-gravitational acceleration, made a light sail, perhaps of natural or even technological origin, a plausible explanation that should be considered. The reaction was a firestorm. Many scientists criticized the idea as premature, arguing that extraordinary claims require extraordinary evidence and that an exotic natural explanation was still more likely than an alien artifact. The debate over Oumuamua became less about a single object and more about the scientific method itself. How do we handle truly unprecedented data? Do we limit our hypotheses only to things we have seen before, or do we allow for the possibility of something entirely new, even unsettling? Oumuamua is now gone, speeding back into the interstellar dark, taking its secrets with it. It left behind no definitive answer, only a profound question etched into its fleeting visit. When the next scout arrives, will we be ready to see it for what it truly is? The search for life beyond Earth often focuses on distant stars, but the most startling candidate emerged right next door. In September 2020, a team of astronomers made a bombshell announcement. They had detected the spectral signature of phosphine gas in the cloud decks of Venus. On Earth, phosphine is a molecule almost exclusively associated with life. Anaerobic microbes in swamps, marshes, and even animal intestines produce it. There are no known natural, non-biological processes on rocky planets that can create it in the quantities the team claimed to see. The implication was as bold as it was simple. If this detection was real, it could be a biosignature, a chemical hint of microbial life floating in the temperate, acidic clouds of our sister planet, a world long written off as a hellish pressure cooker. The image was irresistible, a vision of tiny, resilient organisms living a balloon-like existence 50 kilometers above the scorching surface, in a layer where temperatures and pressures are almost Earth-like. The excitement was instantaneous and global. Here was a potential discovery not from a light year away, but from our nearest planetary neighbor, a place we could theoretically send probes to within years, not millennia. That initial thrill, however, immediately collided with the rigorous machinery of scientific skepticism. Other research groups around the world dove into the data. The original detection relied on a complex analysis of observations from two powerful telescopes, the James Clerk Maxwell Telescope in Hawaii and the Atacama Large Millimeter Array in Chile. The signal was faint, sitting right at the edge of what these instruments could discern. Critics argued that the team might have misidentified the spectral line, confusing the fingerprint of phosphine with that of sulfur dioxide, a common gas in the Venusian atmosphere that has a very similar signature. Others questioned the data processing methods, suggesting that the statistical techniques used to pull the phosphine signal from the background noise might have created a phantom, a ghost in the algorithm. The debate played out in scientific journals and conferences, a public, technical, and sometimes heated discussion over pixels, wavelengths, and error bars. It was a masterclass in how modern science works, not through proclamation, but through relentless collective interrogation. Follow-up studies poured in, each applying different analytical techniques to the same raw data and to new observations. By 2021, the consensus began to shift. A reanalysis by several independent teams concluded that the signal was not phosphine after all. The spectral line was more likely explained by sulfur dioxide, or was simply statistical noise amplified by the processing. The European Space Agency's Venus Express orbiter, which had studied the planet for years, found no supporting evidence in its archived data. The boomerang signal, as it came to be known, had swung out with incredible promise, only to swing back as a probable mirage. Yet this story is not a failure. It perfectly illustrates the essential, self-correcting heart of the scientific process. An extraordinary claim was made, and the global community subjected it to the most intense scrutiny possible. The result tightened our methods and raised the bar for future biosignature claims, especially for Venus. It also refocused attention on a long-overlooked world, sparking a new wave of proposed missions to directly sample its clouds. Sometimes the most important signal is not the one that says hello, but the process that teaches us with painstaking clarity how to listen. The search for a biosignature on Venus hinged on a single, contested line in a spectrum, a ghost in the light. But from the heart of our own galaxy, a different kind of phantom began to broadcast, one that switched on and off like a faulty street lamp in the cosmic night. In 2021, a radio telescope in the Australian outback caught its rhythm. The signal was catalogued under a sterile name, ASCAP J173608, 321,635, a string of numbers pointing to a spot just a few degrees from the galactic center. At first, it seemed like just another transient blip in the data, but as astronomers watched, its behavior became increasingly bizarre. This was not a steady pulsar's heartbeat or a fast radio burst scream. It was something stranger. For weeks at a time, the signal would flare into existence, shining brightly in radio waves, only to vanish completely for months. Its on and off switch seemed utterly random, following no predictable schedule that anyone could decipher. Then there was the nature of its light. The radio waves it emitted were highly polarized, meaning they were oscillating in a single, clean plane. This is a telltale signature of emission generated by an intense, ordered magnetic field, like the kind found around neutron stars or black holes. Yet when telescopes across the globe, including the Meerkat Array in South Africa, tried to find it in other wavelengths, infrared, optical, X-ray, they found nothing. The object was radio loud and completely dark in every other part of the spectrum. This made it a true cosmic orphan. It was not a pulsar which pulses with metronomic regularity. It was not a magnetar which typically emits X-rays during its outbursts. It was not a flaring star which would glow in visible light. It defied every known classification in the celestial catalogue. The leading hypothesis points to a new, theoretical class of object, a galactic center radio transient. Perhaps it is an ultra-long-period magnetar, a neutron star with a magnetic field so strong it only erupts in rare, sporadic radio tantrums. Or maybe it is a binary system where a low-mass star is being slowly devoured by a dormant black hole, with the infalling material creating sporadic, focused radio jets. But for now, ASCAP J173608 to 321,635 remains simply that, a name and a set of impossible properties. It is a reminder that even in our own galactic backyard, amid the stars we think we know, there are still things that turn on, stare directly at us with a focused radio eye, and then simply blink out, leaving us in a silence more profound than any noise. The galactic phantom that blinks on and off is a mystery of absence, but other stars hold secrets written in an unexpected kind of light. A different kind of search is underway, one that scans the cosmos not for radio pulses or chemical traces, but for stars that are missing something. The Gaia spacecraft, a European mission creating an unprecedented three-dimensional map of our galaxy, provides the perfect data for this hunt. Astronomers are using its precise measurements to look for stars that emit far more infrared heat than they should. The theory behind this is both simple and staggering. Imagine a civilization so advanced it seeks to harness the entire energy output of its sun. physicist Freeman Dyson proposed that such a culture might eventually build a vast swarm of orbiting collectors, a megastructure often called a Dyson sphere, that would encircle the star and capture most of its visible light for power. The waste heat from all that captured energy, however, would have to go somewhere. It would be irradiated as a telltale glow of infrared light. So, the search is not for the structure itself, but for its thermal signature, a star that shines brightly in visible light but has a powerful, unexplained infrared excess, like a brilliant light bulb wrapped in a warm blanket. Gaia's immense catalogue has revealed a handful of such candidates, stars whose light profiles show this intriguing imbalance. The immediate and most probable explanation for each one is not alien engineering, but a colossal natural dust disk. Young stars are often surrounded by thick, warm rings of debris left over from their formation, and these rings glow brightly in infrared. Even old stars can have dusty disks created by the grinding collisions of asteroids or the slow evaporation of comets. In every case so far, these natural, astrophysical phenomena are the overwhelmingly likely culprit. Yet the theoretical exercise of the Dyson sphere search is far from pointless. It forces us to think precisely about what a Kardashev Type II civilization might look like across interstellar distances. It defines a specific, detectable signature that future, more sensitive telescopes can watch for. And it reminds us that the most profound discovery might not be a message, but an anomaly in a star's energy budget, a line on a graph that says something here is using the light, not just bathing in it. A single ghost particle from deep space delivered an invitation to a cosmic monster. In September 2017, an observatory buried deep in the Antarctic ice called IceCube detected a neutrino of staggering energy. Neutrinos are the universe's phantoms, nearly massless particles that pass through planets and people with barely a whisper of interaction. Catching one this powerful meant it had a story to tell. For the first time, scientists could trace its incoming path back to a point of origin in the sky. The trail led directly to a known object 4 billion light-years away, a blazar designated TXS 0506+056. A blazar is one of the most violent engines in the cosmos, a supermassive black hole at the heart of a galaxy, devouring matter and firing a pencil-thin jet of radiation and particles directly at Earth. This was the moment multi-messenger astronomy was born. IceCube sent out an immediate alert, and within moments, telescopes across the globe and in space swiveled to stare at that single patch of sky. The Fermi Gamma-Ray Space Telescope saw it blazing in high-energy light. Radio observatories confirmed a surge of activity. The neutrino was not a solitary clue. It was the key that unlocked a coordinated view of a cataclysm. By combining the ghostly neutrino signal with the blaze of gamma rays and the roar of radio waves, astronomers confirmed something profound. Blazars are cosmic particle accelerators on an unimaginable scale, capable of hurling not just light but matter itself across the universe. This single detection solved a century-old mystery of where the highest energy cosmic rays come from, while simultaneously opening a new window on the universe. We are no longer just stargazers, we are now particle detectives, using every form of cosmic messenger to piece together the stories of the most energetic events in creation. The universe's most violent events scream in gamma rays, a light so energetic it can only be born from annihilation. For over a decade, the Fermi Gamma-Ray Space Telescope has been mapping this invisible sky, cataloging thousands of brilliant sources. Yet for hundreds of them, the map ends there. These are the unidentified gamma-ray sources, points of extreme power with no face, no name, and no explanation in any other color of light. They are cosmic sirens wailing from the dark, and we have no idea what is screaming. Each one is a profound mystery. When Fermi detects a bright spot of gamma radiation, the first step is to point every other telescope we have at that same coordinate, searching for a counterpart. Does it pulse in radio waves? Then it might be a pulsar. Does it glow in X-rays? Perhaps it is a black hole binary. But for these hundreds of orphans, the search comes up empty. Optical telescopes see nothing. Radio dishes hear only silence. They are ghosts in the gamma-ray spectrum, present only in the language of pure, raw energy. So what could they possibly be? One leading suspect is a hidden population of pulsars, specifically millisecond pulsars, the spun-up remnants of dead stars that have stolen matter from a companion. These cosmic flywheels can be incredibly faint in other wavelengths. Their beams of radio or X-ray light perhaps pointed away from Earth, while their fierce gamma-ray glow sprays in a wider cone that we do see. They could be the silent majority of stellar corpses in our galaxy, revealed only by their most lethal emission. A more exotic possibility ties directly to the universe's greatest unknown. Some of these unexplained sources could be clumps of dark matter. Certain theoretical models suggest that when dark matter particles collide and annihilate, they could produce a burst of gamma rays. If a dense knot of this invisible matter lurks in just the right place, its self-destruction might appear to Fermi as a steady, unidentifiable glow. Finding even one such source would be a revolution, finally giving a location and a potential signature to the ghost that shapes the cosmos. Then there is the most thrilling option of all. These blank spots on the multi-wavelength map might represent something entirely new, a class of high-energy object we have not yet dreamed of. Perhaps they are the engines behind the most powerful cosmic rays, or the remnants of rare stellar collisions so violent they leave behind only a fading gamma-ray afterglow. Each unidentified source is a door to a territory completely uncharted, a reminder that for all our cataloging, the high-energy sky remains a frontier of pure discovery. The Fermi catalog is not just a list of what we know, it is a map of our ignorance, and its blank spots are where the next revolution in astrophysics is waiting to be written. These unidentified gamma-ray sources are points of pure, screaming energy, but sometimes the universe whispers in the shape of a question. In 2019, astronomers mapping the sky in radio waves stumbled upon something that defied geometry itself. They called them odd radio circles, or ORCs, and the name is a perfect fit. These are not points or blobs, but faint, perfect circles of radio emission, glowing like cosmic smoke rings on scales so vast they are almost incomprehensible. Each one is hundreds of thousands of light years across, larger than entire galaxies, and they exist only in radio light. Point an optical telescope at their centers, and you see nothing but empty space, or perhaps a single, quiet galaxy sitting at the very heart of the ghostly ring. It is as if someone dipped a celestial bubble wand into a vat of radio waves and blew a series of perfect spheres into the intergalactic void. The discovery was so startling that the initial reaction was to suspect an instrumental glitch, a ring-shaped artifact in the data. But the circles persisted across different observations and different telescopes. They were real, and they were everywhere, a new population of cosmic structures hiding in plain sight for decades, waiting for our radio eyes to become sharp enough to see them. The leading natural explanation is as violent as the structures are serene. One theory suggests they are the titanic shockwaves from a catastrophic event in the central galaxy. Perhaps a starburst so intense it blew a spherical bubble of particles into the surrounding space, or the echo of a merger between two supermassive black holes, sending out a ring-shaped tsunami of energy. Another idea posits they are the throats of theoretical wormholes, the mouths of tunnels through space-time itself, glowing with the radiation of particles caught in their gravitational whirlpool. Yet each explanation strains against the sheer, perfect symmetry of the circles. Shockwaves from chaotic events are rarely so flawlessly round. The truth is, ORCs are so new that astronomy lacks even a basic vocabulary for them. They are a reminder that discovery is not always about finding an answer to an old question, but about stumbling upon a question we were not yet smart enough to ask. They hang in the dark, these impossible rings, silent invitations to rethink everything we know about the shape of space and the echoes of cosmic violence. Perfect symmetry in the sky is a profound clue, but the greatest discoveries often lie in what we have not yet seen. The next generation of instruments is being built not just to find answers, but to find new questions we cannot yet form. Two colossal projects stand poised to redefine our cosmic perspective. In the dry, clear air of northern Chile, the Vera Sea, Rubin Observatory is preparing for a mission of relentless vigilance. Its cornerstone is the largest digital camera ever built for astronomy, a 3.2 billion pixel eye that will photograph the entire visible southern sky every few nights. This is not a telescope for studying a single object, but for watching the whole cosmic theater at once. It will create a living, breathing movie of the universe, detecting changes in brightness, position, or appearance for billions of celestial objects. When a fast radio bursts host galaxy flares, when a star like Tabby's begins its strange dimming, or when a new interstellar object like Oumuamua streaks through our solar system, Vera Rubin will see it, catalog it, and alert the world in near real time. It will turn the sky from a static portrait into a dynamic, unfolding story. Meanwhile, on two continents, an even more ambitious era is taking shape. The Square Kilometre Array, or SCAR, will not be a single dish but a forest of them. Its core stations will spread across the remote plains of South Africa and the deserts of Western Australia, linked together to form a single radio telescope with a total collecting area of, as the name suggests, 1 square kilometre. This gives it a sensitivity hundreds of times greater than any current instrument. The SKA will hear whispers the universe has kept secret until now. It will map the cosmic dawn, the moment the first stars switched on after the Big Bang. It will trace the magnetic skeletons of galaxies and test the very fabric of Einstein's spacetime. For the search for signals, its power is almost unimaginable. It could detect airport radar levels of transmission from planets orbiting the nearest stars. It will sift through the radio static of millions of galaxies, listening for the faint, structured murmur of technology. Where current telescopes catch the universe's screams, the SKA will be tuned to its conversations, its sighs, and perhaps its deliberate calls. Together, these instruments represent a fundamental shift. We are moving from an era of stumbling upon mysteries to an era of systematic, all-seeing surveillance of the cosmos. The next wow signal will not be a solitary note scribbled on a printout, but one event in a vast symphony of anomalies, instantly cross-referenced with a billion other points of data. The future of cosmic mystery is not about waiting for a signal to find us, but about building a net so vast and so fine that nothing, not even the quietest whisper from the deepest dark, can slip through. From solitary shouts to repeating whispers, from phantom particles to perfect rings, the cosmos speaks in a language of chaos and precision. We have listened to the death cries of magnetars and the thermal signatures of theoretical megastructures. We have chased ghosts in old data and watched stars vanish behind clouds of impossible dust. Each of these 25 signals, whether finally explained as a kitchen microwave or still lingering as an interstellar enigma, serves the same profound purpose. They are pressure points on the boundary of human knowledge, places where our understanding of physics and reality flexes, strains, and sometimes breaks. A mystery is not a failure of science, it is its engine. The unexplained radio hum that fades under scrutiny teaches us how to listen better. The bizarre chemistry of a distant star forces us to rewrite our catalogues of cosmic elements. Every dead end is a signpost pointing toward a new path. This incredible diversity of phenomena reveals a universe that is not a silent, static void, but a vibrant, noisy, and violently creative arena. It is a place where black holes sing in gamma rays, where neutron stars keep perfect time, and where dark matter may yet announce itself in a frequency we have only just begun to scan. The greatest lesson from all these signals is not that we are alone or that we are being watched, but that we have only just begun to hear the conversation. The universe is far stranger, more active, and more mysterious than we ever dared to imagine from our quiet planet. And the next great discovery, the signal that rewrites all the textbooks, is not a matter of if but when. It is waiting for us right now, hidden in the static between the stars. If you want to be there when we find it, subscribe for more deep dives into the universe's greatest mysteries. And tell us in the comments which of these 25 signals captured your imagination the most.